Picture this: glaciers grinding down to sea level at the equator. Oceans still under ice so thick that sunlight could not reach the water below. Temperatures colder than the last ice age. This frozen world lasted not for centuries, but for millions of years. This happened at least twice in Earth history. Scientists have known about these Snowball Earth events for decades. But one question remains: how does a planet with natural climate stabilizers freeze completely? Recent research offers a compelling explanation for how those deep freezes could have happened, and it changes how we think about Earth's climate stability. The answer was hiding in plain sight in something so small, most of us never even think about it. Something that drifts unseen in every ocean on Earth. It is a hot summer day, and you set your thermostat at 25 degrees Celsius. That's 77 Fahrenheit for the Americans. The air conditioner keeps things steady. But what if that thermostat suddenly overreacts? Not just cooling the room to 25 degrees Celsius, but plunging it to 4 degrees Celsius, 39 Fahrenheit for the Americans. That, researchers say, is what Earth's climate system could do under certain ancient conditions. For decades, scientists have thought our planet comes with a built-in stabilizer, a rough weathering cycle that prevents temperatures from swinging too far out of balance by pulling carbon dioxide out of the air, locking it into rocks, and slowly restoring the planet's balance over hundreds of thousands of years. Yet, evidence from past Snowball Earth events, when Earth may have frozen over entirely, hinted that something else was at play. New research from researchers at the University of California, Riverside has now identified the potential missing piece. Understanding how this system behaves gives us powerful insight into how climate responds to rapid change. Picture the world hundreds of millions of years ago. Oceans stretch across the globe, filled with microscopic plankton. Volcanoes release carbon dioxide into the air and rain absorbs it, forming carbonic acid that slowly dissolves the rocks, a process known as chemical weathering. As the rocks broke down, rivers carried both the dissolved carbon, now in the form of bicarbonate, and the nutrients like phosphorus to the sea, where the carbon eventually settled on the seafloor as limestone. This process acted like a slow-motion balancing act. When geological activity added more CO2 to the air, the planet warmed and weathering sped up, pulling carbon back out of the atmosphere. When CO2 levels fell and the planet cooled, weathering slowed, allowing these geological sources to rebuild it. Together, these opposing forces worked to keep Earth's climate in check. But if this were the only system at work, Earth should have remained relatively stable. Sometimes warmer, sometimes cooler, but never wildly off course. Yet, the rocks tell another story. At least twice, Earth froze so completely that glaciers reached the tropics. Something had pushed the thermostat into overdrive. The question was how a process that usually keeps the planet stable could sometimes do the opposite. The usual weathering cycle operates over hundreds of thousands of years, but buried in the sediment and seawater is another player that reacts much faster: organic carbon. The researchers wanted to know if this overlooked part of the carbon cycle could explain those extreme swings. And here's what they did. The team used a model to simulate what might happen if a massive release of carbon dioxide flooded the atmosphere, similar in scale to what ancient volcanism could have produced. At first, the expected happened. The world warmed. More rain fell, weathering sped up, and nutrients like phosphorus poured into the oceans. Plankton fed on those nutrients, multiplied, and pulled carbon dioxide out of the air through photosynthesis. So far, so good. But then the loop tightened. As plankton died, they sank, carrying carbon to the seafloor. Normally, that burial locks carbon away for millions of years. But in a warmer, more productive ocean, plankton blooms became so intense that their decay consumed much of the available oxygen. That warmer water can hold less oxygen to begin with didn't help either. But here's why this is important. Oxygen normally acts like a glue. keeping phosphorus trapped in seafloor sediments by holding it to iron minerals. But when oxygen ran low, those iron compounds broke apart and released the phosphorus back into the water, fueling yet more plankton growth, which trapped even more carbon dioxide. The simulation showed this feedback clearly. Carbon dioxide levels did not just return to normal, they dropped far below the starting point. Within 100,000 years, Earth's temperatures plunged to levels where global glaciation could have been possible. The very processes that help stabilize the climate sometimes amplified the response instead. The thermostat did not simply steady the room, it reacted powerfully to the initial disruption. How strongly it reacted depended on the world it operated in. Back then, Earth's ocean held far less oxygen than they do today. With so little oxygen to lock phosphorus in the seafloor, more of it kept cycling into the water, driving explosive plankton growth and pulling even more CO2 from the air. The result was dramatic. Global cooling could exceed 6 degrees Celsius, more than the difference between now and the last ice age. Life in these frozen worlds would have been harsh. Glaciers reached the equator, and the oceans lay still beneath thick sheets of ice. Survival likely depended on microbial oases near hydrothermal vents or rare patches of open water. But, as you well know, nothing lasts forever. Over millions of years, carbon dioxide from geologic processes built up again, warming the planet and melting the ice. But the scars of these cycles remain in the rocks we can find today, glacial deposits found in what were once tropical regions. These cycles of runaway cooling and slow recovery show how dynamic Earth's climate system really is. It is not a simple seesaw, but a complex machine with multiple gears that sometimes runs smoothly and sometimes responds dramatically to disturbance. What about today? Earth today holds far more oxygen, which weakens the runaway phosphorus feedback. The overshoot effect is much less likely now, but the principle still matters. When we release carbon dioxide by burning fossil fuels, we trigger the same long-term balancing forces that once pushed the planet toward extreme cooling. As carbon slowly becomes buried again, those forces could, over tens of hundreds of thousands of years, bring the next ice age sooner than expected. It may unfold slowly, but life and climate have always been linked. Here's the powerful part. We are the first species in Earth's history to understand these mechanisms as they unfold. We can see the gears turning. We now know the thermostat works. And that knowledge gives us something no other life form has ever had: the ability to make informed choices. Earth's climate is not governed by a single steady thermostat. It has multiple switches, some tied directly to life itself. Plankton, oxygen, and phosphorus may seem small, but together they have shaped whether our planet baked or froze. This research reminds us that climate is not just a system of rocks and gases. It is alive and responsive, shaped by life as much as it shapes life in return. At Climate Ages, we believe that when we understand, we care. And when we care, that's when we protect. We're releasing carbon dioxide faster than any natural event in Earth's history. But unlike ancient eruptions or plankton blooms, we can observe, measure, and respond. The question is not whether the thermostat will react. It is what we will do with the knowledge of how it works. The power lies in understanding, in action, and in the choices we make right now. Subscribe for more science that explains our past and shapes our future. Did you know that Climate Ages started as a science storytelling newsletter that now has over 12,000 subscribers? Visit climateages.com and join a community of optimistic changemakers. I can't wait to see you there.